Hello, good morning. I am D.K. Panda from Ohio State University. This is a presentation together with my colleague Dr. Jiawi Lu, but he couldn't come due to some personal constraints. So I will try to cover this. So the broad objectives of this talk: how to design cloud environments for high performance computing. So that is the kind of the broad goal. Here we will try to see. As many of you know, I mean, we are in a very exciting phase. I mean, the cloud computing is becoming very common. People want to use all different kinds of resource utilization and have flexibility. But then how do we get high performance computing? Like traditionally people have used it on the local systems. So how we can make a convergence between these two fields? So these are some of the drivers. As you can see in the current generation systems, we have multi-core, many-core system, high performance interconnects like InfiniBand, Rocky. They support this SR-IOV. And then we are having all these SSDs, object storage. These are the newer components which are coming to the system, and also people use very large memory nodes. So the question is like how we can take advantage of all these latest technologies and still trying to provide you very good performance in a cloud environment. How many of you are familiar with SR-IOV? Quite a few, that is very good. So this is the SR-IOV, which stands for single root I/O virtualization, is providing new opportunities to design the HPC cloud with very little overhead. So broadly, if you see here, what happens is like it allows basically a single physical device or a physical function to present itself in as a multiple virtual devices or virtual functions, and then the VFs are designed based on the existing non-virtualized VFs, and then each VF can be dedicated to a single virtual machine through the PCI path through. And this works with both like a 10 gig, 40 gig InfiniBand and also the modern Rocky environment. So if you take a look at very broad objective, like how do I design very large scale clusters with virtualization and then also try to get good performance, you will come up with a lot of like a list of, these are like the wish list. First of all, we need the virtualization support, and then this is where like some of the red lines, this is what I will be trying to focus on in this talk, what we have been doing. So that means first we need some good virtualization support, communication coordination in order to deliver you the best performance. And I will also talk about a little bit about locality-aware communication. That is a very fundamental thing. When VMs are moving around, how do you detect that who is talking to whom? And if we can detect that, we can try to provide you very good performance. And then of course, nowadays like there are all different combinations are coming like VMs, then we have containers running on VMs. So these are the kind of the nested virtualization. We also trying to provide you support, and how we can also provide migration support, especially InfiniBand, how we can migrate InfiniBand connections over the virtual machines. And then of course, on the HPC systems, many times you would have seen like we have resource managers like SLURM. So how we can bring like SLURM together with our kind of solution. So I will try to touch some of these things. So this will be like the outline of the talk. So this project we have been carrying out for many years. And a lot of the solutions what I will be talking about is already publicly available. I will go you over this pointer. I will first start with this. This is our project called MVAPICH2. I will also introduce very soon. So that is I had a virtualization support with SR-IOV and IBSMEM. We have support for either standalone or OpenStack version. So then I will introduce this VM migration support, also support for containers, both Docker side as well as Singularity side. And then I will go into some of the challenges in the nested virtualization and how we can actually integrate very tightly with the SLURM, pure SLURM alone mode or SLURM from OpenStack. And then I will try to give some examples. We have been working with some application people just to see how to deploy these kind of things. So we have been working with some neuroscientists, and these people have a very kind of a need that they should be able to run things from laptop to even to very large clusters. So we are trying to enable them through this HPC Cloud, our solution, so that they can run it on the laptop as well as on very large cluster. And then finally, I will try to touch two additional things in my group we have been doing, which is like more high performance big data like the Hadoop, Spark, Memcached, those kind of stacks, and how we can also move those into the cloud. Okay. And finally, I will touch base on this OpenStack Swift. So that is the software which is also becoming very important in the object store environment. So how we can bring RDMA kind of designs into that. So that will be the overall outline of this talk. So this is the high level overview of the MPI project. Some of you might be familiar. This is a high performance MPI library. This project we started almost day one of InfiniBand. Like in the year 2000, if some of you go back in the history, InfiniBand started in year 2000. In my group, we were working earlier prior to that on the proprietary interconnect like Myrinet, Quadrix, those kind of things. So when InfiniBand came in, we just jumped first, and then the first version was actually introduced at Supercomputing 2002. The library was introduced, and then since then we have been steadily going on. This project is like, as you can see, like from the release point of view, 16 years and going very strong. In addition to the basic version, we also have a lot of optimized versions. So mostly I will be talking today about this virtualization support. So I have a special optimized package for HPC Cloud, and these libraries are now currently being used by more than 2,900 organizations in 86 countries. These are based on voluntary registration. Anybody can just download. This is the site. We have a link kind of thing saying, okay, if your organization would like to be listed, please indicate. So a lot of people download without indicating anything. That's fine with us. But these are the registered organization, and we are coming more like a very close to these days 500,000 downloads from our site. We'll reach in another few months. But it's not just the number of downloads. We have been working with the community, the HPC community over the decade. So these are the systems. If you take a look at the November 17 ranking, even the top #1 system in China, 100 petaflop system, is actually using our stack. Similarly, the largest Omnipath system in the Oak Forest packs in Japan, which is 9th ranked, that is also using our stack. And also the list goes on. If you see a lot of top 500, and we are also, our stack is also available. A lot of if you download the Red Hat, SUSE, OpenHPC, a lot of those stacks, you will see our stacks are there. Okay, so we are trying to enable all these large clusters as they are coming to get the best performance, and these are all production quality code we have been able to push through. So that is the broad overview of the project. So then we started working on, it has been several years back, trying to see how to bring performance, especially with SR-IOV, once Mellanox introduced the SR-IOV on the InfiniBand side. So as we have seen earlier the SR-IOV, so now if you see let's say within the node, these days there are a lot of cores, and then when VMs are running, they will be able to communicate. So first we tried to optimize that intra-node communication. Okay. So this is where we try to bring an IBSMEM module with shared memory, so that the VMs can actually talk to each other very fast instead of going over the network. Very simple solutions people use, I have multiple VMs, they go over the network and come back, but that's like a loop back, you don't get good performance. Traditional MPI stacks have used a shared memory, kernel based communication, CMA, there are a lot of solutions are out there, and we try to exploit those kind of things. So then the question, once we had the basic design, so these are the kind of the papers, as you can see, starting from 2014, we have been publishing, and once we publish these designs, we actually take it into our release, software release, do very in-depth testing, and then push it out. So one was to establish this kind of a communication path. So this is the kind of the new module we introduced, IBSMEM, so that the different VMs can actually efficiently do the communication. But then what we did is, it is think of let's say these VMs are running, as I earlier said, the naive perspective is that they go over the network. Okay. Now let's say VMs also migrate. Okay. So let's say I have two situations, multiple VMs are running on the same node. If they can detect that they are running on the same node, I can switch back the communication. Instead of going through the network, I can push them through IBSMEM or some other mechanisms. Or let's say there was a VM running on another node, and then that VM got migrated to my node. Can they detect that now they are running on the same node? And if I can do that, instead of the InfiniBand communication, I can switch to the local intra-node communication. Okay. So those are the kind of the techniques we introduced. So we had a locality detector, and then the communication coordinator, and then we put it all this together, and it has a native design as well as the OpenStack design. So then what does it give us? Okay. So now if you see this kind of application based number, these are like graph 500 and then the spec MPI. There are 3 bars here. These numbers are taken on the Chameleon cloud, that is the United States NSF National Science Foundation, the research testbed for cloud. So there are 3 bars. So if you see it, this is the like the light blue bar, that is our basic MVAPICH2. You don't have to do anything, just download our basic stack and then run it. It will run, okay, because it's a over VMs it will run, but it may not give you the best performance. That's what you will see here. That is has always the highest time. So these are the time, the higher means not so good. But then the right one, that is the gray, which stands for the best performance you can achieve without any virtualization. That is your dedicated cluster. Okay, no virtualization, nothing. You are just running it on your local lab or any machine. That is the kind of the best we can achieve. So now, if you take a look at this difference, that difference has been higher depending on the applications, and if especially more communication happens, you will see that the gap is larger. So I always tell a student saying, if you put this kind of solution, it will run, but it's not high performance cloud. It is like a low performance cloud, LPC cloud, okay, instead of HPC cloud. Of course, nobody wants LPC cloud, you want always an HPC cloud. So then the middle solution is ours, that is the optimized stack, as you can see it in the orange one. So now if you take a look at this orange and then the gray, the performance gap is very small, 1%, 2%, even in the very worst case, where in the spec MPI gap GeoFM, we do like a 9.5% degradation. Okay, so this is how we are able to like bring all the solutions together, so that when it run on an virtualized environment, you should be able to get performance very close to what you have been getting on your local and dedicated cluster. Okay. So that is the kind of the first solution, and again, all these solutions are available. You should be able to download and try it on your system, except the second one, but all others are available. So now let's talk about the migration. Okay, so that is like as you know, the virtualization always comes with the migration. So now the question is how we can do live migration with SR-IOV device. Okay, and this was the work, like if you see here, it's just trying to show a snapshot saying this is the Infin controller on the Mellanox, and then we are trying to actually migrate here with this kind of a command, so that it gets migrated. So to allow this, we have actually the entire design was presented at the IPDPS conference last year. If you are interested, you can go into more details on this. And this has a lot of steps. This shows the overall architecture. Not only we have that IBSMEM module, what we discussed earlier, but here we have multiple components, like we can have a network suspend trigger mechanism, then read to migrate detector, then network reactivate notifier, migration done detector, and then migration trigger. So we introduce several of these modules so that it can actually go through the very smooth things. When the migration happens, I disconnect and then again start the connections on the other end. And then we also enabled some of the internal to MPI stacks. If some of you know, like there is a progress engine, then we had a progress engine based solution as well as a migration thread based solution to put all these things together. So now if you take a look at how the performance comes here, so what we are trying to show, like in the left one, it's like the breakdown of the VM migration time. So what we are showing on 3 things. One is a TCP, then this is the IP over IV. Some of you might be aware, like if it is a Infin network, you can actually run TCP IP stack, that is through the IP over IV emulation, but then the rightmost is the RDMA design. So that is our design, and we have done like all these breakups, and mostly you will see this is the migration time. So that's what doesn't make a big difference between TCP and IP over IP, but if you do this RDMA, that significantly reduces that time. That is for like a one migration, and in the right hand side, we are trying to show multiple VMs are getting migrated, like 2 to 16 VMs, and then you can say like instead of doing sequentially each one of these in the proposed migration framework, we should be able to cut down the migration time. And this shows actually on live what is happening is like a migrated VM from one machine to another while the benchmark is running. So it's a very simple like a point-to-point latency benchmark you can run, and then so the connection is changing, and here this is where the live migration is happening. You can see this like a latency test, this is like a broadcast tests are happening, and between like all these different solutions have different kinds of trade-offs here. So then the question is like, let's say you are running an application and then you are trying to do this, the migration, how much overhead does it add to your environment. So here what we are showing, this NM is like the no migration. Okay. So that means the system is running, everything is fine. So that is the best performance you can achieve. And then these are the kind of the other solutions what we have proposed, like a progress engine based and the migration thread based, some ORs typical, but overall you will see there is not much overhead. We should be able to, like, again in a real system you should be able to migrate and you will not see any real impact. These are like NAS tests, these are some Graph 500, these are the typical benchmarks we use on the HPC side, and you should be able to use the framework. So then we moved ahead to, so once the basic solution is there, then we started also looking at different kinds of the container environments. As you know, like containers, we have not only the Docker, also Singularity, and broadly you see these are the kind of the two trade-offs, the typical hypervised virtualization, but then the container based virtualization to provide the lightweight virtualization solutions. So in this case again, we try to look at like what are the issues and challenges and then the approaches. So again, our objective is the performance. So where the bottlenecks lies, can we propose some new designs, and can we get that near native performance, just like I proposed in the SR-IOV, similar kind of things we wanted to achieve here. And we took broadly the similar kind of solutions, like we have the locality-aware based design, and here also in the shared memory, typically in the MPI stack, in addition to the shared memory, there is also these days a kernel module called CMA. It is called cross memory attach. So most of the Linux kernels, you will see this is the module is available. So instead of like making a user level copy, you can ask the kernel to make copies. Okay, and that is good for very large messages. So we are able to put all these things together. So this was like, this paper was presented in 2016. So once again the story goes very similar, like if you see those three graphs, the three bars I indicated, like this is the default container, this is the native, and this is the optimized container. So now you can see the performance gap between the optimized container and then the native is very close. Okay. So that means you should be able to actually use our solution to get the very close to the native performance. Here it is trying to go, these are very latest numbers, we on the latest platforms, we have done some studies, like these are the not only the Haswell, but also on the KNL, that is the KNL from Intel, Knights Landing architecture, and we have enabled this support here. It is through Singularity, and again once it shows like there are different trade-offs here. This is like the here you can see these are the internode performance, and this is the intranode, and then intranode again between native and Singularity when you go through it. And here again you can see that when you go through it, Singularity you have less than even 7% overhead, and similar kind of things we also see it on the right hand side. Of course, there are some crossovers here, but those crossovers are nothing to do with virtualization. Those are between internode and intranode, because kernel processors are very slow. So you get this kind of trade-offs, and any MPI stack does some intelligent scheduling or thresholding to see how to design these protocols. So finally, here you will see that this is like the Singularity solution. In fact, we presented this complete solution the last year at the UCC conference. It got the best student paper award. So once again, here you will see like compared to native, if you do go through the Singularity, you almost get very close to the native performance. So that means you can actually use this in a very production environment. And in fact, we have been working with some of the supercomputing centers in the NSF Exceed environment. So they are trying to deploy these on their system. So then the question is like those are the easier ones. Then we moved it to this nested virtualization. So what does this nested virtualization means? That means we are trying to have containers over VMs. Okay. So it is not only like the hypervisor is there, then the Docker engine there are containers, and then there are the VMs and VM2. Okay. So now if you take a look at this, so now instead of like a one layer, now we are introducing multiple layers of communication. Okay. The next slide actually illustrates that much more clearly. So, if you take a look at this, like this is a VM, then we have a container 0, container 1, and this is VM 0, then VM 1. There are multiple communication paths. Okay. So here if you see like this is a NUMA 0, NUMA 1, this is typically 2 sockets node, and typically the Intel one, it is connected with QPI. And so here you will see, let us say across the core 4 to 5, this is like intra VM and intra container. Okay. So that communication is happening within the container, but also it is within the VM. Whereas if you go here like cores 13 to 14, so that is happening intra VM, but it is inter container. So the communication is going across the containers. Similarly, then you can have 2 other combination, which is inter VM container like between 6 to 12, and then internode inter container. So that is actually from 15 to let us say another node. Okay. So then if you want to get the best performance, so you have to optimize all these 4. Okay. So that is the bottom line kind of things. So then what we try to do, earlier I had indicated about this locality detector. Now we had to extend that into 2 levels, 2 layer design. So that is what here it shows, like a container locality detector, then we have a VM locality detector, and then we put it together saying having a nested locality combiner. And then once we have this, then we can actually see which container is running where, which VM is running where. So as long as we get that information, then we can coordinate from our MPI stack design, whether you want to use the CMA channel or some shared memory channel or network channel, we can intelligently select which one to use. So that is the 2-layer NUMA-aware communication coordinator. So this design was actually presented at the VE conference last year. And now if you take a look at the performance, so here it is trying to show the latency and then the bandwidth. The lower is better here, higher is better here on the right hand side. So this is intra socket. So now you can see like this is a little bit dense graph, but if you see the default, that is like the blue line, just out of the box. If you take our MVAPICH2 stack and run it, it will give you, may not give you the best performance. Whereas if you take a look at like the 1 layer, it does not do well, but the 2 layer, that is our design, you can see like that is able to reduce the compared to the 1 layer, 2 layer delivers around 84% benefits in the message latency. And for large messages, here you can clearly see like this is the 2 layer line that is able to push the bandwidth almost 184%. Okay. So then this is that is the intra socket. So this is the inter socket. Similar kind of performance here you will see. 1 layer has similar performance to the default, 2 layer has near native performance for small messages, but there is some overhead on the large messages. And then we had some hybrid designs also trying to combine some of the internal schemes, and there we see around like 42% or 25% benefit. So then, so those are the micro benchmark results, but now if you take a look at some of the application based number, so we have the default, then 1 layer, and then this is the blue line, that is the best, and here it is like application based execution time. So the lower is better. So as you can see, like a graph 500 or like a class D NAS, the final solution is able to give you very good performance benefits compared to the default. Okay, that is what most of the people run, but we have been able to give you more performance through these designs. Excuse me. So those are the kind of the basic communication enhanced schemes, and then we also looked at how you can try to also integrate with the resource managers. Okay, because in a typical cluster you also have the SLURM kind of things run. So we have 2 solutions here, SLURM alone and SLURM with OpenStack. So what we have done is in the SLURM, many of you might be knowing like there is a SPANK plugin. So based on that we have done this plugin based design. So we have 3 components here. One is a VM configuration reader. So as you start the MPI jobs, it reads, registers all the VM configuration options, sets the job control environments, then it actually does the VM launcher, and that also has like 2 options, file based lock, and then it does a unique ID assignment. And finally, when the job runs through the SLURMD, we can also do the VM reclaimer.
So that is the basic, like a basic SLURM. So if you are not going through any OpenStack, that is the kind of solution you can have. But we also have a SLURM SPANK plugin with the OpenStack. So this is how all the flowcharts look like. So we have the OpenStack daemon here, and then this is the where you try to do the VM configuration reader. And then after that you try to do the VM launcher and then the VM reclaimer, and then the OpenStack daemon is actually interfacing with the other SLURM component. That paper was presented in the EuroPAR conference in 2016. So even with that, we also again tried to study the exactly similar things, like are we able to gain the performance at an application level. So the storyline is very similar to the earlier ones, but here the focus more was on how the jobs get allocated. Okay, because in a typical HPC cluster, you can have different job allocation schemes. So we tried to evaluate on 3 different things. It's like a exclusive allocation sequential job, or shared host allocations concurrent jobs, and then the here it's the exclusive allocation concurrent job, because many of you might be knowing these days the number of cores are increasing. So sometimes on the same node you don't run it in exclusively one job, multiple jobs can share. That is what we are trying to say, study the benefits here. So we studied all these different modes. So this was done with the 32 VMs across 8 nodes, and once again you can see we are able to our solution is able to give you very close to the what you can get with the native deployment. So those are the kind of the solutions what we have, and then as I indicated, just to illustrate like one kind of an application domain. So we have been working with some neuroscientists, as many of us know. I mean, this is like a typical might be our image brain kind of thing. Like a MRI, we sometimes go to the MRI machines. People take the scan and they want to understand. I don't understand all the details there what they do, but here we actually tried to come to them because they needed some like a real solution, so that they can take the HPC approach and then try to accelerate their work into the cloud. Okay, so they should be able to, any of the neuroscientists can try these things on their laptop, and then might be go to their department cluster or go to any of the public cloud, and they should be able to run it, and how they can do easy to use. So this is some very detailed maths I want to skip. They do a lot of like a matrix vector computation. In fact, it's very amazing. I mean, so we sometimes in the scientific computing we are so much geared towards matrix vector and all. So the same thing the neuroscientists also do. So we converted that into an MPI based thing, because they were running on a sequential. So this was a sequential application. They even didn't know how to parallelize it. So we worked with them. First we converted them into an MPI. And then if you take a look at these kind of things, so for them, like these numbers are taken on an Intel KNL, even in a single node. Think of a single node. Intel KNL has so many cores, but they were not able to take advantage of this. Okay, so if you have an Intel KNL, they were running out in a sequential mode. Okay, and that was taking almost here 4,000 seconds just to even do some initial processing. It's like a what 10 hours, right? And then we are able to work with them to convert into a parallel version, and then here you can see like we are able to give them like a 8.7x speed up. Okay, so it's exactly they were using the same resource, but they were not able to parallelize, and then we are able to convert that. And in fact, we have a Docker containerized version. I'll show some performance in the next slide, and it is available on the we call it MPI Live, that is the live code, and then we have an MPI version of that. You can actually download either from our site or even the Docker site. We have made it publicly available, so people should be able to download and then run either on your laptop to even to the high performance cluster. So here we studied, like for this was a very concrete application. Then we tried to see whether having it running in different modes, like a 1 container mode or 2 container mode, are we losing any performance or not? The answer was no. I mean, it's more or less 2 container is giving a little bit of benefits, but again through the native whatever like a native cluster you can do, or a single node KNL you can do. You can also do the similar things through the Docker environment, and you don't lose anything.
Okay. So, then let me move into like these are the purely HPC MPI kind of things. In my group also, we have been doing a lot of work on high performance big data. I do not know how many of you are familiar with this project. I know your Stig is familiar. Are there other people familiar with this project? Okay. So, these are like we call it high performance big data. So, the idea is that these days like if you take pure big data like Hadoop, Spark, those are the kind of the stacks which get widely used, and these stacks actually most of the time runs on TCP/IP, the kind of environment. So, the idea here in this project has been how do we move into all these modern InfiniBand, RDMA, Rocky kind of solutions, so that you get the best performance. So, that is the project is HighBD, and so what we have done over this is like a 5-year-old project. So, we have RDMA for Apache Spark, Apache HBase, Memcached, Hadoop. 1.x was we started with that, but now it's the Hadoop 2.x is more common. And then not only we have the basic stack, we also have some plugin stacks in that domain. Actually, a lot of organization use like a Hortonworks or Cloudera. Those are the distributions. So, what we have done is we have plugins so that those stacks can run. You just use our plugin that the network and I/O part is being accelerated. Okay. So, you do not have to totally throw away those stacks, you can use it. So, that itself is like very widely used, around 285 organizations from 34 countries are using. We have more than 26,000 downloads. So, this is available not only for InfiniBand, it is also available for Rocky. It also can run on Ethernet. So, this is like a superset of the Apache stack. So, the Apache stack can only run on Ethernet or over InfiniBand in the IP over IP mode, but here we are able to give you in the RDMA version. So, this is again available for x86 and then the open power, and also available for Singularity and Docker. Actually, this was a little bit older, it is already released. I forgot to change that. So, the way what we have done, it is just exactly what I tried to show it to you in the MPI world. So, we have done like if you take a look at like this is the Hadoop stack. So, we have the HDFS like the Hadoop distributed file system, Hadoop common. So, we have introduced these dotted boxes. So, it is a virtualization aware block management, container allocation, policy extension, task scheduling, topology detection module, exactly what we did on the MPI side. We are able to move it into this. And then now, if you can see similar kind of benefits here, you will see like these are some applications like a cloud burst, which is a genomics application. This is a self join. So, if you see the RDMA Hadoop, that is the red line, and then the blue line is the virtualized version. Okay. So, in fact, the virtualized version we are able to give much more improvement in compared to the basic version. And then finally, this is the project which was just started recently, like 1.5 years old, that is the OpenStack Swift. How many of you have done something with Swift? Okay. So, it is basically a distributed cloud based object storage. It is deployed typically as a part of the OpenStack installation. If you take a look at the communication stack, it is basically HTTP based, and most of the time like they are used to. So, we have the like the proxy servers, these are the different object stores. So, we are able to you access the data from those object stores, but underlying you always see like this is based on the traditional TCP/IP sockets communication. So, the idea here is that how we can bring the high performance networking like the RDMA, InfiniBand, Rocky kind of things here. So, this design was actually presented at CC Grid conference last year. So, what we have done here, the most of the times what you will see that the proxy server becomes the bottleneck. Okay. So, we try to ask that question saying how we can modify that to have a very good design. So, we introduced 2 designs. So, this is like the Swift architecture. So, we have a D1 like a client oblivious design. So, we are only making changes on this side, the proxy, how it communicates to the object server, because we do not want sometimes the clients to get modified. Whereas, the other one which is more integrated design, that is the D2, which is like a metadata based design. So, here again we try to, instead of client talking to proxy server and then getting all the things, client can directly talk to the proxy server here. The red lines are the RDMA lines.
and then the blue line is the standard TCP/IP communication. So, for some of the communication paths, we are able to move them from the standard TCP to the RDMA based design. And now, if you take a look at the performance, so this is like a some common operations in the Swift get and put. Those are the basic operations. So, here if you take a look at these are the latency, the lower is better. So, this is the basic version, and here we are trying to break up into like communication, I/O, some hash sum, where the time is going, and here you can see that the D2 design is always giving you the best performance. Okay. And the right hand side, so this is the put breakup, and then this is the gate latency evaluation. So, here you can see we are able to reduce even for large like a 2 gigabyte, 1 gigabytes or 4 gigabytes, we are able to reduce the time by 64%. So, this is still in the research, this has not been released yet, we are trying to have some more enhancements into this design. And as some of these designs have been coming out, I indicated either you can download our stacks and then deploy it on your system. We have actually made some of these appliances, converted them to appliances. So, this is appliances available on the Chameleon cloud. I indicated that this is the US NSF based research test bed. So, broadly we have like there is a MPI bare metal cluster complex appliance, and then we also have an MPI SR-IOV module. So, even as an end user, so all these things are been converted into appropriate scripts, and also as an end user you just select your appliance and then click, and then things will get deployed. So, all these things whatever I indicated earlier have been converted into appliance. So, I will encourage you to download some of these things and try it on your on the Chameleon cloud if you have an account, or otherwise you can exactly do similar kind of things on your cloud environment for your users to take advances with. So, with this let me conclude here. What I showed here like starting with the MPI, so especially the MVAPICH2 virtualization library has a lot of these features. It can actually provide very good performance for standalone as well as OpenStack, SLURM and SLURM plus OpenStack. It supports virtual migration, supports that exactly is being worked out in the release, but everything else is being worked out, is available, and there is very little overhead with virtualization. So, you can really get the what I indicated like trying to truly combine high performance computing HPC with cloud. So, you can go to this website and you should be able to download our stack from there, and I also demonstrated like how you can take the cloud technologies to applications like neuroscience and big data environment, and also the big data appliances kind of thing, whatever is available on some of the public cloud, you can also do it yourself. So, with this let me finish here. I just want to indicate this for the last 2 years we have also been from our group trying to lead a forum here in the community saying how we can design these efficient clouds for HPC, big data and deep learning. So, we had the first BOF at SC Supercomputing 2017. We will have one more, the second edition will be at the ISC in Frankfurt. So, if you are going there at ISC, it will be on June 27th on the Wednesday. So, I will invite you to come and attend this BOF and share your thoughts. Okay. So, with this let me close here. These are all our pointers. So, if there are any quick questions, I will be happy to answer now, or we can discuss offline. Yes, please.
So, if I'm understanding the design elements correctly, a lot of this, or many of these things are optimizations without any regard to security.
Yes.
So, I mean, in an environment like Chameleon and most recent environments we support, that's great. But what would you recommend for like an approach for a secure,
Yeah. Okay. Okay. So, the question let me repeat if you did not hear. So, what he said is like the current solutions are like how it works with the security kind of constraints. So, what we have done here is like we do not change anything with the security, it is like these things are all complementary designs. Okay. So, if you have anything running like let us say basic Infin infrastructure has the security support, this should just complement to here. Okay. So, there are like we are not changing any paradigm here. Okay. So same thing in a Rocky environment, if you have the things, or in a Swift environment, whatever your security modules will be able to directly interact with these things here.
You had with the Swift thing completely bypassing the proxy server.
Yeah, so that's why we give two things. You see, so that is the whole idea. Like we have a D1 and D2. So in the D1, then if you are so much concerned about the security, then just use the D1 model. Okay. Whereas if some people have their own other solutions, or they want to trade off the performance with some security, or they have a private things, then they can go for D2. That is exactly the reason we have.
For reasons of security, like, okay, well, as good as it's ever going to be, we're going to leave that one alone, or do you continue to pursue enhancements and improvements?
We are not security expert. Okay, that's why we don't jump into that and then come up with some solution which security community may not be buying. But we'll be very happy to talk with you or somebody else, trying to see up to what level things can be taken or pushed, saying, yeah, we are not sacrificing anything in the security, but still able to exploit the performance. Okay. Yes, let's take.
How did you add RDMA transports to Swift?
How did you add means?
Design, I mean, are you basing this on Python services?
I may need to check with the student. Okay, I can discuss with you offline. So you are trying to see that, like, exactly what layer. I'll be able to answer that later on. Okay, thanks. Any other question? Okay, so if not, we are exactly, I mean, we finished at the lunch time. So have a nice lunch, and then I'll be happy to talk with some of you. Thanks.